This is a review of page 5 of the semester review packet. And the first thing I want to do is review heating and cooling curves. So you've got energy being added or removed going across this axis, and this is temperature. So let's say you're heating up some ice. You heat it, it eventually melts. You heat it some more as a liquid, it eventually boils, and then it can heat up as a gas. So in the reverse direction, the cooling curve, it condenses, cools down as a liquid, it freezes, and then it cools down as a solid. So I'm going to put an S for solid. I'm going to write in melting here. L for liquid. This is boiling. This is a G for gas. So of course in the reverse, that's still a gas. This is condensing, going from a gas to a liquid. There's the liquid again. This is freezing in the opposite direction. And now you've got your solid cooling down. So things to think about. What's happening at the molecular phase? When something's heating up, like on all of these parts where it's not at a plateau, I'm going to call those points A, this is B, C, this is D, and E. So on the heating curve at A, C, and E, particles are speeding up. That's their kinetic energy that's going up. But it's different at points B and D, the plateaus. At those, particles move apart, so the distance between them gets greater. That's potential energy that's going up. So all of these areas require energy to happen. Or in the reverse, energy is being lost or removed in order for something to freeze, for example. So that's going to set the foundation for us to work through these problems. One other point I want to make is we're going to be talking about the formulas Q equals MC delta T, as well as Q equals delta H fusion times moles, and similarly delta H vaporization times moles. So one thing that students get confused about is they don't know when they cannot use Q equals MCAT. And you cannot use this to calculate how much energy it takes for a phase change to occur. You cannot use them at these points. No. All right. And that's because there is no temperature change from 0 degrees to 0 degrees. If you plugged a 0 into this equation for delta T, the answer would just say 0 energy, and that's not true. So these two equations are for the phase changes. This top one is for freezing or melting, and this bottom one is for boiling or condensation. Notice there's no change in temperature. There's a constant, and then the number of moles that you're trying to melt or freeze or boil or condense. A sheet that's helpful to have out during all of this is your table of specific heats, which of course you're going to have for the final. Okay, so let's take a look at some problems. For this heating curve, what is the melting point? So melting is occurring at this bottom plateau. Right here, I'll circle it. So the melting point, therefore, is right at 0. The boiling point is at this second plateau right here. So that's 100. What's the freezing point? Kind of a trick. It's the exact same as the melting point. Where is the temperature changing? It's changing at number 1, number 3, and number 5. Where is the potential energy changing? Remember, that's where molecules are getting further apart. That's at 2 and 4. Where is there a change in kinetic energy? It's the same as number 38. It's where the temperature is changing. Number 41 says, as the substance goes through point 2, what's happening to the distance between molecules? It's increasing. Because at point 2, it's going from a solid to a liquid. So the molecules that were once really close together are now moving further apart. And now they can slide past one another, and that's what gives a liquid its properties. Then it asks you to draw a heating curve for a substance that's heated. And for this weird substance, the melting point's 10 and the boiling point's 95. It says label the states of matter. So we're starting at negative 25 degrees Celsius, so I would label this temperature degrees Celsius, and it goes up to 125. And other special points are 10 degrees and 95 degrees. So it heats up, it melts, it heats up, it melts, it boils, and then it heats up again. So here it's a solid, here it's a liquid, here it's a gas. And it said also label the melting and the boiling. The states of matter during the phase change, this is both a solid and a liquid. Similarly, during boiling, this is both a liquid and a gas. Then for 43, it says calculate the specific heat of copper. And it gives you mass, change in temperature, and energy. So that should kind of make you think, okay, I must be doing something with Q equals mc delta T. And remember that Q is energy, or heat energy, and that's measured in joules. M stands for mass, and that's in grams. C stands for specific heat. And the units for this one are interesting. It's how much energy it takes to change the temperature 1 degree Celsius of 1 gram of that material. So every material has a different specific heat. So if I go back to my little chart here, notice it takes a lot of energy to change 1 gram of water 1 degree Celsius, 4.18 joules. But something like lead, it only takes 0.13 joules to change 1 gram of lead 1 degree Celsius. So different materials have different properties. And of course, delta T is the change in temperature. Okay, so let's do this problem. It's asking you to solve for specific heat. So how do we get specific heat by itself? We've got to divide both sides by m delta T. So if we do that, C is by itself. So now we got to plug this in. So Q's on top, 850 joules, divided by the mass, which is 95, times the change in temperature. And this will come out to be just the units we want, joules per gram degree Celsius. So it comes out to be 0.6 joules per gram degree Celsius. That is the specific heat of copper. What about the one below it? This one's even easier because you don't have to do any rearranging. It just says how much heat, so it's asking you to solve for Q, would be required to raise the temperature of mercury 52 degrees. And you've got 250 grams of it. Well, we need the specific heat for mercury. So you've got to go to your table of specific heats, and it said it was liquid, and that's 0.14. So then we go back and we've got to plug in 0.14. Joules per gram degree Celsius. I'll show you how the units cancel out. And we're increasing the temperature by 52 degrees. So degrees Celsius cancels out, grams cancels out, we're going to be left with joules. Multiply these. It takes 1,820 joules to heat up that mercury. Now we're on 45. How much energy is required to freeze 100 grams of ethanol? This should really say how much energy is required to be lost, or it should say how much energy is released when 100 grams of ethanol freezes. It's kind of poorly phrased. So Q equals delta H fusion times moles. We need a different equation because this is not changing in temperature. This is saying, how do we go 0 degrees Celsius liquid ethanol to 0 degrees Celsius solid ethanol? So it says the heat of fusion is 4,600. Just as a random side note, it says for ethanol on here that it's 5,000. So maybe this is a rounded number. Anyways, we can go back here and let's use the value that they give us just because it's simpler. So 4,600 joules need to be released to freeze 1 mole. Then we've got to go back and figure out how many moles of ethanol are we trying to freeze. 100 grams of C2H6O. How do we get grams into moles? We divide by the molar mass. So once you add that up, it adds to 46.06 grams. So 100 divided by 46.06 comes out to be 2.2 moles. Multiply that together and we get our answer. It takes 10,000, or you need to release 10,120 joules of energy to freeze that ethanol. Last problem on this page, this is a good one. It says a student collected data from a calorimetry experiment. And I always ask, have we done that in class? Yes, it's when we burned food. So there's a can of water, and in this example, you're burning butanol underneath it. And you're measuring how much energy that water absorbed. It's 1,400 grams of water, and it's going up from 21.5 to 27.7 degrees Celsius, while 13.7 grams of C4H10O burned. We're going to make the assumption that the energy released by the butanol while it's burning under that can is equal to the energy absorbed by the water. Why? Because it's easy to calculate the energy absorbed by the water. We can just use Q equals MCAT. The mass of the water, 1,400. The specific heat for water, check it out on your sheet, it's 4.18. The temperature change here, it's going up by 6.2. Multiply that together and you get 36,282 joules. That's how much energy the water absorbed. The question says how many kilojoules are produced per mole of butanol. Well, this is how much total energy was produced in joules. How do we get that into kilojoules? We divide by 1,000. That comes out to be 36.282 kilojoules then. But we need kilojoules per mole. So we've got to take 13.7 grams and divide it by the molar mass of C4H10O. That's 74.1 grams per mole. That comes out to be 0.185 moles. So then for our last step, we just take kilojoules divided by moles. So we're going to do 36.282 divided by 0.185. That butanol released 196.1 kilojoules per mole as it burned. And that's it for page 5.